So it can be done. It's probably harder. Like, you know, when you have one cut line, it's probably a little easier to think about. And those two NVIDIA dice could be like mirror images of each other. And so you only lay out one die. If you do, that's a clever idea, rotating it. So the only one that I know of that's done that is Xilinx. So Xilinx/AMD has done it for one of their recent really big FPGAs where they made it out of 4 pieces of silicon. And they did it in a 2x2 grid. And the reason they did it in a 2x2 grid is they said, we'll talk a bit more about FPGA interposers later in the course, but you can only get, even with an interposer, you can only get a fraction of the wiring across the cut line. So they found it was better to have one cut line in each direction than to have, you know, say 3 cut lines in the same direction. They didn't give any real evidence of why that would be true, so you could think about, does that make sense to you or not? But that's what they did. Okay. So let's switch back to FPGAs. Okay, so some administration. So test next week, October 21st. Start a class, so we'll start at 5:10 here, and just how you spread out and write it here. It's worth 10% of your final mark. And I know you're like, well, wait a sec, does that mean I don't have a lecture? Don't worry, you get both a test and a lecture, right? So it's full value, right? You're paying a lot of tuition. So what does it cover? The lecture material, the non-optional readings. I won't ask you anything about an optional reasoning, and assignment 1 and 2. I'm not going to try to ask you like really tricky questions, but basically I'm also not going to guarantee like, for sure, don't bother doing the assignments. I won't ask any questions. Like there might be something that relates to something you did on the assignment, but it's not going to be something super tricky. Yeah.
How long roughly will the test be?
So we have to make it. So, but you know, half an hour to 50 minutes, not that long. We're not planning to make it super long. Probably closer to like half an hour than to 50 minutes, but I guess we'll see. If people need time, I'll give them, I don't want to make it like a sort of time crunch kind of thing, so we'll give you like plenty of time to write it. Does that make sense? It's closed book, it's on paper. Yeah, basic goal, are you paying attention? Not like to be super tricky, which I guess is always said. That doesn't mean like, oh, I don't actually have to read over the notes. Probably a good idea to read over your notes. So. Okay, reading for next week. So we won't talk about either of these this week. This is probably the most important reading of the course. It's like a survey paper on FPGA architecture. So the second part of the course, we're kind of following some of this. You only have to read pages 4 to 15 for this week. I can't remember why I left out the first few pages. Reading the first few pages as like setup might be a good idea too. And we'll do the second, it's a long paper, so we'll read the second half of the paper later on. So if you want to read the whole thing, we will read it all eventually, but this questionnaire just covers the first part. And this is another paper that's basically how do you design low-level FPGA circuitry, so transistor-level design. And it's useful to know how do you actually build the circuitry that goes in an FPGA. Okay, so what are we talking about today? So we kind of switched from how do I use FPGAs, how do they compute other devices, and now going more into like really what's inside them. So today we're going to talk about like different styles. How can I organize an FPGA? And let's see, mostly I'm going to draw some pictures. So I think I'm just going to turn off the projector now. Yeah, let's see. Yeah, I think it's better to switch up the projector. Okay, so there's kind of like two major parts of an FPGA. There's like how do the blocks work, and the most important block is the logic block. So we're going to talk about the logic elements, then we'll talk about the routing. And then modern FPGAs also embed other hard blocks in as well, which we'll talk about later. But the two kind of fundamental things in an FPGA are the logic elements, how do we make it logic, and then the routing. Those have been around for a long time. So let's talk first about what are our options for logic elements. Okay, so let's go all the way back to the first things that could be called programmable logic. Okay, this is way back in the 1970s. we had what's called programmable read-only memory. So you basically take inputs, we've got n of them, you put them into a decoder, and the decoder is going to output 2 to the n outputs. Okay, so these are like word lines, basically. Okay, I've got a whole bunch of these, right? 2 to the n of these word lines, and I've got some number of outputs, say m outputs. Okay, so I've got n inputs, I've got m outputs, and so far I haven't actually shown anything programmable. So the way this works is you could have a fuse here, and this fuse has not been blown out. So if I set in a certain input pattern, say I set in all ones, then the decoder is going to activate this top line. That's going to turn on this transistor, which is going to pull down this wire. Okay? If this piece of metal is still there, this fuse still exists, it's going to pull down this signal. I'm going to get a logic 0. Because these are weak pull-ups up here. Okay, so you intentionally make, these transistors are permanently on, okay? But I'm going to make this weak. Small width, large L, maybe high threshold voltage, so it doesn't pull up very well, but it will pull this up to VDD if nothing's fighting it eventually. But if I sent in a 1, 1, 1, and then this basically, therefore, is turned on, it's going to pull down this wire, and this piece of metal is going to result in this output line getting pulled down, because it'll overwhelm this. The way this is programmed is we actually have the ability to blow fuses. So I can destroy that fuse, and now it's an open. So now this line won't get pulled down. So I'm going to get a logic 1 on that. So I can basically program this by blowing and not blowing certain fuses. So you need a programmer that can do that, and circuitry inside the chip that can do it. And this is the first form of programmable logic. So how does the area grow with n? It's my number of inputs, and m, my number of outputs. Because that's going to tell me if this is like a highly scalable solution that I can just keep using forever. Right? We keep making transistors smaller. Can I keep just using this architecture and getting more and more logic capacity? So yeah, how does the area of this scale with n and m? What do you think? Okay, so how would you write that? So area is order, right? So it's 2 to the n. So it's exponential inputs, which is pretty bad. And then what happens with outputs? Just multiply by m, right? Yeah, so the outputs are not as bad. So basically, this was quite successful, but it's not scalable. Also, it didn't do sequential logic. Now, we could fix that by adding some flip-flops in here and some ability to go around them, but we didn't. People didn't because it just didn't scale well enough. I mean, you can still use this for small functions. We don't usually use ROM, but you can actually use this same idea with a RAM, right? You send in your inputs, you read out some data. People still use that in circuitry today, as long as the ROM doesn't get too big. So it's a known FPGA design technique of program some relatively large lookup, but not too big, into a block RAM on the chip, and we can actually use this exact same style of send in some data, read out a word, and you could basically do anything you want, okay? And people do that for things like table lookups of relatively large tables. They can actually program it in the block RAMs of an FPGA. It's done with different circuitry, but it's the same basic idea, right? A ROM is a useful way to do logic. Okay, so that was PROMs. Okay, so then the next thing that people came up with was PALs, programmable array logic, which was in the late 1970s. And let's see, let me draw what that looks like. Okay, so my inputs come in here. Okay, and I need some kind of programmable switch. So I'm just going to show an X for those. And then basically, so I can connect into these AND gates, okay? So I can take a bunch of these signals and send them into AND gates. And then those AND gates go into an OR gate. Okay, so basically it's AND OR logic. So you choose what inputs. This is like I1, this is like let's see what I used for my, well, it was like IN minus 1. And I can basically program the true or the complement value to go into some AND gates, and those AND gates then feed into, a few AND gates will feed into an OR gate. To do sequential logic, they also added flip-flops. Okay, and you can basically pick, do I want to be combinational or sequential? And that's my output. And you could also feed these outputs back to the input. And that gave you the ability to do more complex logic functions, because you could do kind of multiple passes through the AND OR array. Okay, so the area of this might be a little harder to analyze. So if I have M outputs, I have N inputs. Basically, the area grew quadratically. And this was often built as a wired OR structure because it was very efficient in area. Okay, so often built as wired OR. Okay, so what does that mean? Let's say I want to make the function ABC. So if I actually built AND gates like this, I would just connect, input A, input B, and input C to the AND gate. So it's really obvious. With wired OR logic, I actually am building everything out of ORs, okay? And I use De Morgan's theorem to basically say that is the same as that, right? So hopefully you remember that from Boolean algebra. If not, you can plug in some ones and zeros and convince yourself this works. So I changed this into an OR logic. And I can build that with a quite area efficient structure. So I got this long shared wire. And I can hook A bar to that NMOS, B bar to that NMOS, well, the gate of that NMOS, and C bar to this last one. And then I want to make sure, okay, so if A is low, this turns on. If B is low, this turns on. C is low, this turns on. So if any one of them is low, I'm going to pull this line to ground, which is actually what I'd like in an AND gate. Now, if they're all high, these are all going to shut off. I'm going to leave this wire floating. That's not good, right? You don't ever want to leave wires floating in a digital circuit because they'll float to unknown voltages and bizarre stuff can start happening if they're connected to anything. Plus, I don't know what this logic value is. So we do the same trick as before. We basically put a pull-up on it. Okay, and this pull-up, this is also a pull-up. The first time I showed it, it did with an NMOS. By this point, people had PMOSs too, so you can do a pull-up with a PMOS in this way as well, right? So you tie the source to the drain, and it'll actually be permanently on. And I, again, want this to be weak. So it has to lose. When one of these turns on, this has to be able to pull this down to ground, right? Because I want a 0. And only if they're all off do I want this to pull up. This actually gets, so that would actually get my output. And then this is going to have not much drive strength, so I'm immediately going to put it through a buffer. So like a pair of inverters, because I do not want this to be loaded by some downstream logic. Okay, so that works. The nice thing about it is for every input, right? If I'm doing a 3-input AND gate, I actually only needed 3 transistors plus 1. If I was doing like an 8-input AND gate, and they often made these AND gates pretty big. So I'm doing an 8 or 12, let's say I'm doing a 15-input AND gate. I actually only need 16 transistors. So it's pretty thrifty in terms of transistors, which makes it a good choice when transistors are expensive. What do you think is what's a key downfall of this nowadays? Okay, so transistors aren't as expensive, so we can throw more transistors at a problem, but we'd rather not. Like, I mean, if we can use fewer transistors, we'd still like to use fewer. Yeah.
Well, it's not like CMOS.
Yeah, it is not CMOS.
So, and all the manufacturing is like CMOS.
Well, I guess it uses CMOS transistors. It uses a PMOS and it uses an NMOS. So it is compatible with CMOS manufacturing. If you're taking a VLSI design course, you can make this today, right? You can put it on your chip, it'll work. There may be, depending on how big your chip is, there may be a problem when it comes back. What do you think?
Because transistors are so small nowadays, is there any problem with leakage?
There is leakage. You have to worry about that. So that means you can't make this pull-up too weak, right? Because if it's too weak, the leakage of this could overwhelm them. So, but you can overcome that. Like, leakage is still pretty small compared to an on transistor. So you're right, it's a design consideration. You have to make this strong enough, but it's still not going to kill you. What do you think?
It will not meet the timing constraints because the pull-up transistor is weak.
Mm-hmm.
So it takes time to charge the capacitors and turn the voltage from 0 to 1.
Yeah, that's actually a good point. Okay, so if I make this pull-up weak, yeah, it pulls up slowly. This wire, also, if I make this AND gate, if I make a lot of, well, it's really an OR gate, but I'm using it to make ANDs. If I put a lot of stuff on it, this wire might get long. If this wire, and wire capacitance now matters even more than transistor capacitance for most structures. So a weak pull-up, pulling up a big wire could be an issue. I still might be, if I can keep this wire short, maybe I can make it fast enough, but it's an issue. I'm gonna have to be careful. It could slow me down. But there's something fundamental, and it's actually speed comes into it. So I don't want it to be too slow, so I don't want my weak pull-up to be too too weak. Now what do we have to worry about? What do you think? Yeah, actually, not even dynamic power. Dynamic power is when you switch, which everything has, right? Like the best circuitry we can make in CMOS still has dynamic power, right? You're going to have to charge and discharge capacitance. What about this? Does this have only dynamic power? What happens if I put, let's say C is 0, okay? So this transistor's on. Okay, so this transistor's stronger, so this goes to 0, right? So this line goes to 0, this is just a buffer, so this is 0. It all worked, okay? So C equals 0, output equals 0. What's happening though? Like what is this weak pull-up doing? Yeah, I mean this weak pull-up's desperately trying to pull up. It can't, okay? It's a weakling, right? It's never going to win this fight, but it's going to burn as much power as it possibly can, right? So for one gate like this won't cause that much power, right? You could go analyze it, but if you at today's integration levels, you repeat this for like 1 billion transistors, and this is suddenly a big deal. This is actually a lot more power than we worry about leakage power, and leakage power is when this is off and this is off, okay? When this is on, but it's kind of a weak transistor, and this is on, we're actually orders of magnitude worse, okay? So, well, at least one order, probably several orders of magnitude worse. So this is a high power solution. So that's kind of fundamental. And the things that I might do to make it a bit less high power are going to make it really slow. So it gets back to your speed, and they're still going to be fairly high power. So basically power was a killer on this. So nowadays you wouldn't use a structure that has a pull-up like that. The wired OR structures like this are still very area efficient, but they're not, if you use a pull-up that doesn't shut off, they're not power efficient. Yeah?
You said often built as wired OR. What part of the PAL is implemented as wired OR? Is it the far right?
So it's basically this. You can implement this AND gate as a wired OR. So this is basically, I've shown 3 inputs to this, but often you'd actually have a whole bunch of inputs going into it. So, imagine there's a lot more inputs here. They're all going down here. And there are switches that allow me to hook up to several AND gates. And to get more logic capacity, you'd actually want to make these AND gates big. If I do it as wired OR, I can basically distribute it. I can actually put these transistors right under here. So I don't really get this sort of centralized AND gate. I actually get this distributed structure that is pretty efficient, right? It's kind of right under the wiring. But not a good idea nowadays because of power. Okay, so C is the lookup table. Okay, or the LUT. Okay, this was actually developed in 1984. Who do you think developed this? Who first came up with the lookup table for programmable logic? What do you think? Yeah, Xilinx did it. Xilinx did it in 1984. It's actually, I never met the person who did this, but I know his name was Friedman because I know the Friedman patents. Because when I was at Altair, I was like, oh, the Friedman patents. So they've now expired. Patents only last for like 20 years or so. But just like a super valuable patent, right? Like you patented the idea of a LUT in programmable logic, and then an entire industry grew up around that. So it actually was a factor in for a lot of, it probably slowed the adoption of LUTs for some of the programmable logic companies because of patent reasons. So anyway, Friedman was a smart person, made a very, very valuable patent. Okay, so how does this work? We've already talked about it a bit, but let me draw it again for completeness. So I build a MUX. I hook its data inputs up to an SRAM. So I'm just going to build a 2-input MUX. Okay, so I've got 2 inputs that come in here to the select lines. I build 2 to the n, or 4. SRAM cells. Okay, so hook up to the data lines. Let's see. Okay, I don't only want to look up tables, so I'm going to hook it into a flip-flop, and I'm going to do the same trick that we just saw, where I can take the output from the registered version of this, or I can take it from just the lookup table itself. Okay, and I'll use an SRAM cell to select that as well. So now everything is, I'm not using any unusual processing technology. I'm just using SRAM. And let's see. Okay, let's say, let's do a quick test of this. Let's say I want to make my output equal to the exclusive OR of my two inputs. Okay, so you guys are using CAD tools. You can just write output equals exclusive OR of the inputs. Let's say the CAD tools are crashing, or let's say the license server goes down. Okay, could happen. So you have to, how do you do this? So what should I put into this truth table if I wanted to get the exclusive OR of the two inputs? So what do you think? What do I put there? Okay, say 0 there, right? Yeah, so just put the truth table of function in. So it can do any function. So it's very powerful. Okay, so how many SRAM cells? If I have k inputs, so I'm going to switch from n to k, because that's what people usually use for the size of a LUT. If I have k inputs, how many SRAM cells do I need? Right, so I need 2 to the k SRAM cells for a k LUT. And k LUT means that many inputs. And implements any function that uses k inputs or less. Okay, so the area of this, how does this grow with the, there's only one output, so that's easy. How does it grow with inputs? It's also pretty easy, given what we just wrote. It grows with 2 to the k, right? So area is proportional to 2 to the k. Because basically I need this SRAM has to grow with that. Also the multiplexer size, like the number of, when you go look at how do you build this multiplexer, it also grows with 2 to the k. So basically everything on this side is going to grow with 2 to the k. Let's see. Okay, and there's another, something that's kind of related to LUTs, but not the same. You can make MUX-based logic elements, and that was done by Actel, which became part of Microsemi, is now part of Microchip. They also use some lookup tables, but they have historically also used these MUX-based logic elements. Okay, so what do those look like? Okay, so they basically build a tree of multiplexers. So this is like a 4 to 1 mux, basically, but I've shown you the internals of it. It's a cascade of 2 to 1 muxes. And if I built you a bigger lookup table, you would say if I built a, well actually this is basically this lookup table, right? If I actually look at this inside this 4 to 1 mux, I would basically see a structure like this, right? A cascade of 2 to 1 muxes. But instead of hooking the data inputs up to SRAM bits, they hook them up to actual signals, so things that can come from the programmable routing. And they also hook the select signals up to the programmable routing as well. Now we did that with this LUT, but we kind of wired these two together, right? We said there's one input that controls these 2 muxes. That's like one of our select inputs, and there's one that controls this mux. So that's what we did with it. And then we hooked up the other data inputs to SRAM. So you can think of a LUT as being a kind of a constrained version of this, right? Where these have to be hooked up to SRAM, and this signal and this signal are just hooked up to like one select input for my 4 to 1 mux. But Actel showed all of these internals. So the other thing that's important to realize, so these are signals that can come from the programmable routing. The programmable routing can bring in ground and VCC as well. Okay, so I can choose to route ground or VCC anywhere I want. So I can also make these things 1 or 0 if I want to. Okay, so let's see what we can do with this. So let's see if I can make this function. Okay, so I want to make a 3-input XOR. So can I make a 3-input XOR out of this 2-input LUT? No, like it's an easy test, right? Wait, 3 is greater than 2. Okay, there is no possible way I could fit this truth table for a 3-input function in here. It doesn't work. Okay, let's see if we can fit it in here. Okay, let me erase this because this is not in the Actel MUX-based logic element. Okay, can you find a mapping of signals? Okay, so I've got A, B, and C. You can use any one of those. You probably will have to use them. It's hard to make a function of a signal if you don't hook it to anything. It's like a magic predictor. So you're going to use these signals, but also remember you can hook things to power or ground. Okay, so how could I hook this up to make that function? Anybody want to take a shot at it? I actually wrote the answer down in front. Like, you get really stupid in front of the board. I was like, I don't think I could do this under pressure. But that's okay. You guys are more used to this. So, yeah.
I would probably try to use A, B, or C as the select signals for the bus somehow.
Okay, but wait a sec. That's like a meta answer. Wait, are you going to apply this technique on the test next week, right? So the question A is do the following. You say, well, I would attack this question by first forming a research plan. And then I would do a set of web searches. So, go ahead.
I would feed it into an LLM.
Well, that is that is the deep research prompt. So, anybody want to take a crack at it? Yeah.
I'll just put like I5, 6, and 7 to ABC.
Okay, so you're going to put I5 to A. Is that right? I6 to B, and I7 to C. What are these? You got to hook these to something.
Yeah, I mean, I'll basically just put them like zeros and ones to get to my output. So I know for XOR,
Okay.
if like 1 or 3 of them are ones,
Yeah.
then I get 1.
So I think you're on the right track. Okay, so let's start here. So you put C on here. So if C is 0, you're going to take this path. Okay? And then if you take that path, if B is 0, you'll take this path. Okay, so what do you want to hook to I1?
That would be 0.
Right, so you could hook 0 to this, right? And let me think about that. 0, yeah, what about A? Okay, so if C is 0, you go through this path. B is 0, you go to this path. You're saying hook it to 0. It means you do not care about A. Right? When C and B are both 0, you got a good feeling. The XOR, doesn't matter what A is. The XOR is for sure 0. So you're actually on the right path, and this is probably the right way to discover this. But what do you want to do then? You're close. You're so close. What do you think?
I guess if B is 0, if B is 0, C is 0, then it's like 0 XOR 0 is already 0, so it would just be whatever A
No,
is.
then I'll just remove the A.
So you're going to take this A away. Okay, you don't want that A. And you can hook A up as many times as you want. Programmer routing doesn't care. You're going to change this to, you put the A there. Right, okay, so now if A is 0, this is 0. If A is 1, this is 1. And that looks right. Okay, so if C is 0, but B is 1, then I get this signal. Okay, what do you want to hook there? And also, it's pretty common that you can, like, assume the complements are available. This actually, yeah, you could do not A. Like when you do this kind of architecture, you have what are called programmable inverters. So basically the ability to invert or not invert. You either do it in the routing or you do it at the inputs. So you can do a not A, right? And so yeah, that's the right idea. And then if you C is 1, you take this path. C is 1, B is 0. What do you want to hook up to here? We've lost him. You're on a roll. What do you think? What do you think? So you want not A on this case? Let me think about that. If A is 1, you want 0. Yeah, not A. And then what do you want here? You want A. Yeah, so you can do it. So this is This should be a B. Yeah, so that's a B. Well, if I have C is 1, I take this path. B is 1, I take this path. If A is 1, I get a 1. But if A is 0, I should get a 0, right? So this one should be A, this not A, A, right? Okay, so this is actually a little more powerful. Okay, so it's basically got this same multiplexer in it. I've just drawn it expanded. And I've got control over all of these internals. And I could do a 3-input function that I clearly could not do with this. Okay, so it's basically, it's positive is it's a bit more powerful than a LUT. Could this do everything that a 2-LUT could do? So what do you think? Yeah, like just by hooking up if I always hook up the same signal to this and a different signal to this. So one input to here, the other input to here. So input 1 goes to here and here, and input 2 goes there, and I just program in the truth table. So I put grounds and VCCs. This is a LUT. Okay, so it can do everything a LUT can do, but it can do more, right? In this case, I was able to actually do another input, a bigger input function. So it sounds better than a LUT. Another positive, if I basically look at what is its area compared to inputs and outputs. So its area compared to if I add all these inputs up, it's 7 inputs. If I was to add one more level to the mux, I would actually increase the area of the mux by about a factor of 2, right? Because I'd have to add a bunch more, like 4 more 2-to-1 muxes. But I would also add a whole bunch more inputs. Basically, I'd also add, let's see, like 7 more inputs. So I'd pretty much double my inputs and double my area. So my area is actually proportional to the number of inputs. Whereas here it was exponentially growing with the number of inputs. So, so it looks pretty good. I guess a negative is that it can't implement most functions that use all these inputs. Okay, so it can implement everything a 2-LUT does, but that basically doesn't use most of its inputs, or most of its inputs are set to power or ground or connected to the same thing. If you give me, this has 7 inputs, you give me an arbitrary 7-input function, it probably can't implement it, okay? But it can implement some useful, like a 6-input function that it can implement would be mux, right? Like you could do a 6-input, well, a 4-to-1 mux, right? And you would actually need 6 different signals to do that, and it could do it. You would basically hook these 2 things to the same select line, and these would all be 4 different data lines. So it can do some useful functions with many inputs, but there are also lots of functions with many inputs it won't be able to do. So far, it looks pretty good for this, though, right? Is there any other downsides to it? Yeah, what do you think, Bear?
I think this is going to put a lot of pressure on the routing end.
Yeah, if you look only at just what I built here, and you said, well, that doesn't look bad. I built 4 2-to-1 muxes, and it can do everything a LUT can do and more. Like, why wouldn't I do this, right? And in fact, I got rid of some SRAM cells. Sounds like maybe it's even cheaper, and it can do more. But these routing ports are actually really expensive in an FPGA. So these are all, we're going to look at how you build programmable routing. But generally, programmable routing is built out of a bunch of prefabricated wires and prefabricated muxes. We'll analyze some of the circuitry so you get kind of intuition for it. But basically, the intuition is these are quite expensive. So think of the number of inputs that you have to hook to the programmable routing as being not a second-order concern, but like the first-order concern. So that's what's bad about this. So it's more routing ports. And those routing ports are expensive. Okay, so what this means is that none of these logic elements really scale to big sizes. You can study a 2-input LUT's actually not a good choice. So it's too small. So you should actually scale it up more than this. And we'll read a few papers about why. But none of them, if you just kind of go, I want to make a really big amount of programmable logic, you can't just scale up one of these logic elements to a huge number of inputs or a huge number of outputs, because their area starts blowing up for all of them. Okay, so that brings us to the second part of an FPGA. So first thing you need to pick, logic element. Second thing, routing network. Okay, so you can't scale any of these to really big sizes, so what you do is you make a bunch of them and hook them together somehow. Okay, so one way you can do that is what's called a hierarchical FPGA. And an example of that still sells, I believe, pretty well today is called Max 7K. Okay, so this is an Altera part that was made many years ago, but still sells a lot of it. Okay, so what that looks like is you have these PAL arrays. Remember, those were these and/or logic blocks, okay, that scale okay, but not great. So we don't build one giant one. We'll build 4 somewhat smaller ones. So smaller number of inputs, smaller number of outputs. But our area doesn't grow as fast, because our area, which I erased, was that these grew, the area of this grew as the number of inputs times the number of outputs. So instead of building one giant one, we'll build 4 somewhat smaller ones. And then we have to hook this together with some kind of switch network. Okay, so I need to be able to send signals out to the switch network. I need to be able to take signals in from the switch network. And the idea is that these 4 things together they together have more inputs and outputs. They can do more logic. Okay, so we're going to group a bunch of smaller logic blocks with a switch network. Okay, so simplest switch network that I can think of is a full crossbar. Okay, so a full crossbar basically can connect any input to any output, and it can do it with basically the same speed. So it's very easy to reason about. There's no blocking. Like, you're guaranteed any output from any one of these can connect to any input of any other one. So that's pretty nice. But how does it grow, right? How well, we're doing this to be scalable. So how much area does that take? Yeah. Right. So it grows, and if my number of inputs and outputs are not the same, it would be number of inputs times outputs, which is basically quadratic, right? It's like if these were both n, that's an n squared growth. There's basically 2 ways to build this, right? You can basically take one way is with like a cross-point network. So I can have my n inputs going across on wires. And I can have my m outputs out here. Okay, so I build n wires one way, I build m wires the other way. And wherever they cross, I put some kind of switch. Okay, maybe it's a tri-state buffer. And I can program an SRAM cell to turn on this tri-state buffer. Maybe I use a pass transistor, but nowadays a tri-state buffer is probably a better choice. So the area of this grows, the number of cross points, right? Like these little tri-state buffers that I put in here grows n times m. Okay, so that's quadratic. Now you might not build it this way. It's actually more common nowadays to build it as, okay, so I have n inputs. I actually build an n to 1 mux. Okay, so all my inputs here go into a mux. and that produces 1 output. So then I have to repeat this m times. Okay, so it turns out if you actually, you're going to see maybe more about how to build multiplexers than you ever wanted to in this course, because FPGAs use a lot of multiplexers. But when you look at how you build a multiplexer, it also grows with the number of inputs linearly. So this is going to be order n area as well. There's a few different ways to build it, but no matter the most efficient ways to build it, this still grows with at least n if you have n inputs, and then you need m of them. Okay, so that's still n times m. So whether I build it with these cross points, or I build it with, these are my tiny tri-state buffers, because usually with these cross points you want to make them small, or I build it with a bunch of muxes, either way, this is going to grow quadratically. Does that make sense? So we can use crossbars. We actually use them in FPGAs, but you can't let them get too big. It's okay to use until n and m get really large, not okay after that. So you can use this with a full crossbar, and that actually is done in some of these Max 7K devices. But if we keep growing it, right? So we keep making more and more of these PALs and trying to connect them together, this switch network is going to start limiting us because it's growing quadratically. So what we can do instead, basically, is we can make a much more complicated routing network. So I'm just going to call that complex multi-stage. There's a lot of ways to make routing networks where you go through many intermediate hops. And you can consider FPGA routing to be like a super complicated multi-stage routing network. And if you do that and you do it well, you can make the area proportional to the inputs plus the outputs. Okay, so I have not proven that, right? That's like an assertion. But you're going to see how we can make routing networks that are much more efficient. And they can at least asymptotically approach that. They are a lot harder to use. Like, this is why we need CAD tools. It's why you need to actually do research into the architecture to figure out, well, what is that complex multi-stage network? It will have blocking. Okay, so a crossbar has this nice property of, I want to connect an input to an output. I just turn on this one switch, or I tell this mux what to select, and it's done. CAD problem's easy, and there's no chance of blocking. It can be done. These complex multi-stage networks, the CAD problem is much harder, right? So it's much less clear what you turn on, and there is blocking, right? So you can have, there is a way to connect this output to this input, but it might not work if I'm simultaneously trying to connect this output to this input. Or if I do, I have to change the internal path. Okay, it would be bad if there was no way to do it. But it would be common that in a multi-stage network, the use of some path to connect this means that this has to take some other path. And then as you do that for like thousands and tens of thousands of paths, it gets quite complicated. And that's why you need a CAD tool, and it's much more difficult to reason about. But it is much more area efficient. So that's why people do it when these switch networks start getting big. Okay, so let's look at what this complex, let's look at one way we can do this. Okay, so I'm going to build like a multi-level sort of switching network. Okay, crossbar, you kind of just turn on one switch and it works. We're not going to make one that's like a multi-level switch. Okay, so this is a logic block, which I'll abbreviate as LB. And what I'm going to do is I'm going to basically go out from this logic block, And I have a couple wires here that go between these two logic blocks. And let's say the blocks have one input and one output. And I'm going to put X's where I have programmable switches. Okay, maybe those are tri-state drivers, for example. And now I can connect my outputs and my inputs, okay, using these two wires. So I turn on the programmable switch. I want to connect one output to one input. Turn on other programmable switches to connect the other output to the other input. And we're going to call that a level 1 wire. So now I want to make a bigger FPGA. So that's only 2 logic blocks. So what I do is I take this structure and I replicate it. Okay, and I put in some more level 1 wires. And now these can talk to each other. To make them talk to each other, I basically put another layer of wiring hierarchy in. Okay, and maybe I'll put programmable switches where these circles are. Okay, so these new wires I'll call level 2 wires. So I only use them when I want to connect a logic block to one that's kind of far away. It's in the other, from the lower part of the chip to the upper part of the chip. And I'm putting fewer of these wires in. Okay, so I had a total of 4 level 1 wires, but I only put 3 level 2 wires in. And that's typically what you do here. So you assume that these logic blocks that are kind of close to each other, the CAD tool is going to try to put things that are highly connected close to each other in this hierarchy. So the number of signals that have to go over to these logic blocks, you hope is less, okay? And the CAD tool's job is to choose where to put these things so that it is less. So I'm just not going to build as many, right? In the worst case, I could actually have 4 signals trying to go from this side to that side. And I'm just not building enough wires for that. If you need that, the CAD tool is going to, well, basically it won't route. Okay, so you're going to have to buy a bigger chip, redesign your logic, get a better placement engine, something. Okay, but that's done to keep it cheaper. Okay, now if I want to go even bigger, I add another level of hierarchy. Okay, so these will be called level 3 wires. And basically I'd mirror this whole thing over here. This whole group of 4 logic blocks, I would just do another one of those. Okay, and I could have had 2, 4, 6, 8, total of 8 signals trying to go across this. And I didn't build 8 wires. I only built 4. So I'm again assuming that the CAD tool does not need to connect distant parts of the circuit as often it needs to connect close parts, so I just didn't build as many wires. I'm also trying to save area, but I'm putting a sparse switch pattern in. So I'm not connecting all the level 1 wires to all the level 2 wires. I'm kind of putting some switches in, but it's not full connectivity. And that's again to reduce area. It does make my CAD tools problem more difficult, right? It has to find a path that goes through this limited set of switches and limited set of wires that, without blocking things. Yeah?
Why would you want to limit the amount of switches if it's like a tri-state buffer that seems pretty cheap to just put it on every node in the sector?
Yeah, so if it is cheap enough, you could just put a tri-state buffer everywhere, right? So there's no hard and fast rule. So as these channels, as these start getting kind of big, like at the upper levels of this hierarchy, you'll start getting large numbers of wires crossing. So they're putting in, 100 times 200, might be 20,000 tri-state buffers could start to hurt. You're right that here, trying to save this many, you might go, I'll just put them in. Does that answer your question? These are done with sort of architecture experiments where you see what the CAD tool can do. And you compare that to how much area am I adding and decide is it a good idea or not. You also, in some cases, if you go, I got nothing to put under here because there's just empty space, then you might say, well, why not put a tri-state buffer in? So, yeah.
Isn't it more expensive than just a tri-state buffer? Don't you also need an SRAM as well as bitstream control to get the data in there?
Yeah, you'll always need at least like a tri-state buffer plus an SRAM. So the tri-state buffer has to know its own configuration. And then they have to be programmable. The programming hardware is relatively cheap because I kind of showed you the general way you do it is you will shift in data in a shift register essentially on the edge of the chip. And then you strobe one basic enable signal. And a whole row of SRAMs will read their data from essentially bit lines. So that doesn't add much to the SRAM. So it's like an SRAM that can be written effectively. But you're right. You can't have in the dominant technology for FPGAs, it's SRAM based, so any switch needs an SRAM telling it what it's doing. Let's see. Okay, so this is basically what's a multi-level switching network, and this is what's used to build hierarchical FPGAs. Okay, and there are a bunch of examples of this. So I'll show you a picture from an academic paper. Andrew DeHaan was one of the people who proposed these kinds of hierarchical structures. It was the dominant Altera FPGA type for quite a while. Altera's Apex and Flex lines. You can buy embedded FPGAs. So an FPGA is an IP block that you stick inside your larger SoC. So one of the companies that sells those is called Flex Logix. Flex Logix or Flex Logic? I think it's Flex Logix. So these ones are kind of older. Okay, Altera has moved away from this style of architecture. This one is current, right, for embedded FPGAs. Okay, so what's good about this? So it's better than using a full crossbar for sure. Okay, so the scale's much better. It's a very valid way to make a chip. But I also told you that Altera, for example, which made some very successful chips using this technique, has kind of moved away from it, which probably tells you there's probably some shortcoming. They probably didn't just do that randomly. So any positives, any negatives you can think of? Yeah.
I guess on the negative side, because you have just many levels of hierarchy, there's no equal hop between the two logic blocks as it's another.
Yeah.
And then you also have very long level paths along with very long hierarchical layers.
Yeah. So those are good points. So that's actually okay. So you said two things. So one is that between two logic blocks, you get this logic block can talk to this logic block quite quickly, but this logic block to talk to something way over here, it's going to be slow, right? Some of that is unavoidable. Okay, there is no technology that can say like a full crossbar could have everybody talk to each other in the same speed, but the full crossbar is just not scalable. Okay, everything else you get differences in delay depending on where you're going. So you're right. But I guess I'm saying that one you can't get rid of. Like all the competing ones have the same thing. But you also pointed out that if you need to go to something far away, you go up through a bunch of wires, and some of those wires get quite long, right? Is that correct? Yeah, so what makes you worried? So you'd rather not go far, but what makes you worried about long wires in particular?
I guess that increases the load path so you can put a cap on the depth maximum to extract out of your chip.
Yeah, so long wires are a bigger and bigger problem. Okay, so when these chips first were proposed and sort of during their heyday, transistor delays were more important and wiring delay gradually became important. At the lower levels here, it's still kind of dominated by transistor delay with some loading from the wires. When we start getting to wires that start spanning a significant chunk of the chip, there's a whole bunch of RC in that wire. So the wire actually, not only is it loading the transistors driving it, it has essentially its own self-loading, like its own RC time constant. And when that starts becoming big, the wire is very slow. And the solution is normally put a buffer in the middle of it. Okay? Putting a buffer in the middle of this starts kind of breaking down the hierarchy, right? Now you were you kind of wanted to connect distant parts of the chip using these wires, but basically the top wires that are quite long are not electrically very good anymore. There are solutions like, well, maybe you could put like a buffer each way, like a programmable repeater, and you could do that, but it's basically, this hierarchy is starting to break down because you can't make it fast enough. And once you start breaking down the hierarchy, there are other options, okay? So if we only knew how to do this, we probably would do stuff like for the really long wires, we'd put programmable repeaters in and so on. We could do better than just making super long wires. But the fact that we're having to do all this stuff to make it not fight physics just sort of points in a different direction. So that really is the kind of number one thing that makes these not scale to really big sizes, is really long wires just have high delay and they need repeaters. So I'm going to write that down in a minute, but I'm going to write down some positives, because otherwise you go, well, this is all just bad. Why did we actually do this? Okay? So one positive for this is that we can place the logic elements or the cells with a partitioner. Okay, so a bunch of you are in Jason Anderson's CAD course. Who studied what a partitioner is already? Or maybe it's at the end of the course now. Has he already gone through it or not?
I did another course last year.
Oh, okay. So you know what a partitioner is. So somebody describe to me what a partitioner is. Go ahead. Yeah.
Sort of create cuts along your fabric and place your elements in different parts of the fabric so that it eases placement and routing later on. You're kind of pushing things into different parts based on where you need to be.
Yeah, so you gave me an answer and a half. So the first part of what you said is a partitioner takes a circuit and chops it in two pieces. Okay, well that's a bipartitioner. That's kind of most classic kind of partitioner. So you take a circuit, you cut it in two pieces, and you cut it in two pieces so that you minimize what's called the crossing count. Like the number of signals that go between the two pieces is minimized. And that turns out to be useful in all sorts of ways. One of the ways it can be useful is in placement, right? So in this case, what we do is we take a partitioner and we'd say, cut my circuit in half. So your circuit is like basically a netlist. Okay, netlist is like a bunch of connected cells that came from your synthesis tool. And you would say, here, let me draw a little circuit basically. And we will put something over here. Okay, so say that's my circuit. A partitioner would, you tell it, cut this approximately in half and don't cut as few signals as you can. It would say, cut it there, okay, because I only cut one signal. So this half and this half are not that strongly connected. And for this style of FPGA, you can use that to inform your placement decisions. You can say, okay, I'll take this part and I'll put it over here in the left half, and I'll take this part and I'll put it over here in the right half. And then I can run the partitioner again. So let's cut it again, and it might decide, well, let's cut it there. Okay, so now that maybe this becomes top part and bottom part and so on. My first cut is more interesting because I made sure that there was one obvious cut for this circuit. The other ones are less obvious. Okay, so why is that useful? Partitioners work well. Okay, it's a part of CAD that's been studied for a long time, and partitioners get good results and usually don't take really long to run. So if I can run a partitioner over and over again and use it to decide where to put things, left half, right half, now cut that piece in half and say top, bottom, it runs pretty quickly and it gets pretty good results in terms of minimizing how many signals go between these. And minimizing how many signals go between them minimizes how many wires I had to build at every level of this hierarchy. So it kind of matches what I want. So basically, why are partitioners good? It's basically good, fast CAD tools or algorithms available. Okay, so that was one advantage of it. Okay, second advantage, it's kind of related to that. It's basically, it matches the hierarchical nature of hardware. Okay, so in HDL, you usually write it, I make component 1, I make component 2, then I might make a component 3 that instantiates one of each of those. Okay, so there's actually a hierarchy in your design. And designers naturally want to have, they try to pick blocks or components where there's fewer signals going between them than inside, right? They're trying to pick related functions, do a bunch here, and then I have fewer inputs and outputs because this was some block of logic that had a reason to be together. That's why I wrote my HDL that way. So it kind of turns out to be a natural property of circuits that as you go up the design hierarchy, things are usually less strongly connected, okay? So we'll take a break for 10 minutes, and then when we come back, I'll actually try to analyze that, and we can see how well does this structure scale. Okay, so let's take a break for 10 minutes, and I'm going to prop these doors open to try to cool this off. Again? Okay, so why is this matching the hierarchical nature of circuits important? Because it leads to this property that the number of wires you need at an upper hierarchy level is less than the sum of the wires you add at the lower hierarchy level. And that basically helps your scalability. So let's look at this. What I built here, at level 1, I have 2 wires. And if I add up these 2 level 1s and these 2 level 1s, I got 4 total wires at level 1. And I only connected them with 3 level 2 wires. And then if I have these 3 level 2 wires, and I haven't shown it, but there'd be 3 more over here, I've only connected them with 4 level 3 wires. Okay, so at every level of the hierarchy, I add up all the wires at the level below, and then I build fewer than that at the next level of hierarchy. And that helps my scalability, right? These upper level wires are expensive, they're not doing logic. At least I don't have to build as many of them. Okay, so that helps my scalability. And this hierarchical nature of circuits and this locality of circuits, that they tend to connect to things that are near them in the design, is important enough that it's actually got a name. It's called Rent's rule. So this isn't like a law of physics. It's just something that happens. It was first noticed by IBM, an engineer at IBM, many years ago. So he found that a large number of circuits followed this rule. So the number of terminals, so IOs, was equal to some constant times the amount of stuff, at that time gates, to some exponent p. Okay? And that exponent p is called the rent exponent. Well, it's defined to be the rent exponent. Okay, so he's empirically found this relation held for a lot of circuits. Okay, T equals number of terminals. Okay, so IOs. And what's interesting about this is that actually the range of P for any circuit that anybody's ever seen is relatively limited. It goes between 0 and 1. I think it actually might be less than 1. Okay, could get asymptotically close to 1. I don't know if I can get to 1 or not.
What is C? It's a constant.
C is just a constant. Okay, so pretty much we don't care about C. Like maybe if I was counting my gates and AND gates, maybe C would be 3, 2 inputs and 1 output. If I was using 6 input XORs, maybe it would be 7. If instead of gates I was doing LUTs, then maybe it would be maybe it would be 5 if I was doing 4 LUTs. So it's a constant to make the math work out. But basically we don't really care about it because we only care about trends. So C is just there to make everything line up. Okay, so let's look at a couple of rent exponents. So let's say P equals 0. Okay, so if P equals 0, what's my terminal count of the circuit? It's like C. Like, it doesn't matter how big it is. Okay, so my number of IOs, if you ask me to make a little piece of circuitry, is maybe 50. And then you say, no, make it 1,000 times bigger. I want 1,000 times the functionality. You say, oh, still only need 50 inputs, right? What about 1,000,000 times bigger? I still just need my 50 inputs, right? So, so that's like super local. Like no matter how much stuff you put in this system, the number of inputs that you need is constant. Okay, so so from a CAD tool perspective or from building interconnect perspective, this is like ideal. This is like your dream system. Okay, so with that one, the terminal count is constant, no matter how big I make the circuit. So can you think of any circuit where that's actually true? Like, is this like something that never exists? I'm not going to ask you yet because you might have cribbed the notes already. Sorry, but yeah. What do you think?
Something like a lookup table to use the exact table.
So let me think about that. A lookup table. So you're making like a giant lookup table, and you're basically saying like that you're just sending in more and more inputs. It would grow slowly. It would grow logarithmically, actually, because I think you're saying you're making one ever bigger lookup table. Is that right? So your number of inputs grows only logarithmically, and you only have one output. So that's true. It would grow not quite constant, but it's a logarithmic growth. On the other hand, you're also getting relatively limited functionality. Like this person says, okay, you make like a 5-input lookup table, and your coworkers are amazed they can do any function of 5 inputs. And then like they give you a budget of like $100 million, you make a giant chip, and you can now do a 25-input lookup table. So it's logarithmic, but the functionality is growing slowly. But that is a good example. So yeah.
Maybe some kind of serializer.
Yeah, so actually, so serializer is a good, like basically something that's a linear chain of processing, which a serializer could be. So if I and these do exist. So if I basically make a chain of blocks, so I make a nice processing pipeline where everybody passes its output to the input of the next block. Okay, so this is, let's say this is I make this block first. Okay, so I make that block, I count my inputs and outputs, and these are buses, but let's just ignore that. Let's say terminals equals 2. Okay, so I've got one input, one output. And then I say, well, that was doing some nice, that sold well, or that was useful. I'm going to make a bigger one. I'm going to do 2 of those blocks in cascade because I'm doing, some signal conditioning or some serializer. So I basically want to do more conditioning on my output. So I double my processing in like a pipelined fashion. And I basically increase my gate count by a factor of 2. But T is still 2. I basically do it again. Maybe I'll make it 4 times as big. So I draw this box around. That's my new system. I still only cut 1 input and 1 output. So T is still equal to 2. Okay, so systems where the rent exponent is 0 do exist, right? Like a nice linear pipeline is a great example. So basically a chain of blocks. Chain or a linear pipeline. Okay, and so in that case, T is 2 no matter how many blocks we make. Okay, why is this good? I mean, if this was the only kind of design that we had to put in this array, we wouldn't actually have to widen these upper channels at all, right? So we need 2 wires here at the lowest level. We need 2 wires at the next level, 2 wires at the next level, 2 wires forever, right? We'll never need to move more than this small amount of signals between any hierarchy level. Our design is going to be quite efficient because we just won't build very much routing at the upper levels of the hierarchy. Okay, but not all designs have a rent exponent of 0. So let's take a rent exponent of 0.5. Okay, so the number of inputs and outputs is growing as the square root of the gates, or the square root of functionality. So can you think of anything that would achieve that? Any style of design, any idea whatsoever? Yeah?
An adder maybe?
An adder? So why do you think an adder? What makes you think of that?
Because it has like one output which requires another input, and it's like a chain of that.
Okay, let me think about that. Okay, so let's take an adder. So if I have an adder, I have a chain. Okay, and then I also am bringing in inputs to add, right? So this is like my carry. Say I'm making a big ripple carry adder, right? So I've got outputs, that's my sum out. I've got 2 inputs. So if I draw a box on this, I get 3 signals. If I draw a box on this, well, actually I guess 4 signals. If I draw a box on this, I get 1, 2, 3, 4, 5, 6, 7 signals. If I draw a box on this, I get, what do you think? 7, 8, 9, 10, 11, 12, 13 signals. So it's growing actually almost linearly, not quite linearly. Because in this case, okay, it is a chain of blocks, but every time I go down the chain, I'm kind of bringing in these parallel inputs. Okay, so an adder's actually, yeah, by itself, an adder is actually growing quite a bit faster than a rent exponent of 0.5. It's almost a rent exponent of 1, which is much harder in your CAD tools. Yeah. Oh my goodness.
A fast matrix multiplying engine.
Okay, look, Gary, look at it. I'm going to take offline because I'm not going to draw the schematic for that right now.
The area grows quadratically with the number of like the number of bits.
Okay, that sounds right. Okay, but I'm going to get you to come up and draw it if you want to draw it. But that makes sense. If you build carry look-aheads, the logic can grow very quickly, and the terminal count doesn't grow that fast. So it's a good example. I have a simpler one. This is a good example, but it's too complicated for me to draw. Yeah.
Well, if the adder is linear, then we can try the multiplier, which should be the right one.
Yeah. So basically, it's things that have a 2D structure. Actually, if you can make a 2D structure where you bring all your inputs and outputs in on the perimeter, then you naturally wind up with the square root. So let me draw a couple of those. So one, well, you're saying a multiplier. Okay, so a multiplier array has essentially, it's hard to draw, but essentially it has a whole bunch of partial products that are cascaded together. So you get n squared compute, and you only need n bits of input. Okay, so if you arrange, so you can, a multiplier is a good example, right? N squared compute, n bits of input. That means your number of inputs is growing as the square root of your logic. Okay, so I'm not going to draw it, I think, but I think a multiplier is a good example. Yeah.
In this case, T, you don't care about the internal signals going from like.
No, so internals are free. That's the idea of Rent's rule is only about what leaves your module. So yeah, multiplier is a good one. Another one is, this is even harder to draw maybe, but a systolic array multiplier. Okay, so one multiplier, if you draw it out, actually has this 2D structure of you bring in like input 1, you bring in input 2, they're each n bits, and you basically compute all the partial products with AND gates. And then you add them all up. So basically get n squared partial products and adders. And you can monkey around with that logic a bunch to try to be a bit faster, but that's fundamentally what you're doing. So that means that if I redefine this to be like z, this is square root of z, right? So it does match this 0.5. Yeah.
I'm just wondering if it's right to think that the lower the rent exponent, the more compute bound.
The lower the rent exponent, like the less your interconnect. And so yes, it is another way of thinking you're more compute bound. Yeah. It's like basically high rent exponents means interconnect is, you need a lot of interconnect, you need a lot of I/O. And low rent exponents mean you have a lot of compute for the amount of I/O that you're doing. So yeah, there's another way to think of it. So, okay, so an individual multiplier matches this. A systolic array, so those tensor cores that we're talking about in Blackwell, the general way that you make that kind of multiplier unit, NVIDIA's never actually published, to my knowledge, exactly what they do, but the usual way you do it is you feed inputs in, and now your inputs are not like one number, it's like entire vectors from a row of one matrix, a column of the other matrix, and they go into a compute array that's doing n squared computation every cycle and gradually shifting this data through as it completes the matrix multiply. So not only one multiplier, but also this array of multipliers that can do entire matrix multiplies sort of has the same behavior of a rent exponent of 0.5. And maybe an even easier one to understand is an SRAM array. Okay, so let's build an SRAM array. We build a whole bunch of bits, and we basically activate them with word lines. Okay, so I've got my word lines here. And when a word line goes high, all the SRAMs in that row connect to the bit line. Okay, so there I've got my bit lines down here, and that's where my output is. So basically, the amount of I/O, the number of terminals I need, it's essentially all in the perimeter. The terminals is, again, proportional to the number of SRAM cells to the 0.5. Okay, and that's part of why, as you make SRAM arrays bigger, their cost per bit goes down, right? The I/Os don't go up. They grow at a slower rate than the actual SRAMs. But basically, anything that has this kind of structure, right? You can make like a square array that's doing compute or storage, and you can get all your I/Os in from the perimeter, is going to have a rent exponent of like 0.5. Yeah, you're going to see like another kind, like when we get to, we're looking at hierarchical FPGAs right now, but basically silicon likes 0.5. Because we're building on 2D silicon, a rent exponent of 0.5 is kind of nice because you make the compute as big as you want, and you're going to get square root more perimeter for I/O. So if your rent exponent is 0.5, you're actually very scalable because you're compatible essentially with what silicon naturally gives you. Let's see. Okay, P equals 0.75. I don't have a picture for this. But control logic often has relatively poor locality. Like you just start connecting states to other states and so on. It just, I don't exactly know why, but it just turns out that when you run control logic through a CAD tool, it will tend to have connectivity that spans larger amounts, basically a larger rent exponent. So for control logic, a random logic, okay, so it means it doesn't really have an underlying data bus that it's trying to implement. It's implementing a bunch of control. Rent exponent of 0.5 is reasonably typical. And this will be considered poor locality. Poor because it's like kind of from the CAD tool developer's perspective. Like people who make chips and people who write CAD tools do not like rent exponents to get really big because it's hard for the CAD tools and it's less efficient for the chip. But I don't have a good picture of that. Okay, so this leads to one of the other negatives of this architecture. So when we build a hierarchical architecture like this, we're essentially, I'm picking a rent exponent. Okay, what I've been doing here is I've been narrowing the channels as I go up, and that is equivalent to I've picked a rent exponent. So I'm thinking, how fast does my I/O count grow as I look at bigger and bigger chunks of logic, right? Like higher and higher up in the hierarchy. And I'm assuming my rent exponent is less than 1 because I've been narrowing the channels. Okay, so I'm growing the number of wires more slowly than I'm growing the amount of logic that's underneath that hierarchy level. And I have to pick that when I make the chip. And then I have to live with it for every design. But you can see different designs actually have different rent exponents. But in an FPGA, I don't get to go back and change it, right? I got to pick once, and it's got to be, everybody's got to live with it. Okay, so I have to pick, let's call it rent exponent of the architecture. Okay, and in this one, I basically picked a rent exponent of 0.5. Okay, so what does that mean? I decided at level 1 that I've got one input and one output from each logic block, so to connect 2 of them, all I needed was 2 wires. Okay, so at level 1, I'm going to use W to mean channel width, but W of level 1 is just 2 wires. Okay, so now how do I choose W of level 2? Okay, level 2, so level 1 I was just connecting 2 logic blocks. Well, one logic block was the amount of logic that I was connecting. At level 2, the thing I'm connecting to, one end of my wires is twice that much, right? There are 2 logic blocks. So I have, for my gate count, I have the constant, okay? My constant was 2, right? So remember Red's rule was T equals C times gate, which is just logic count, to the P. Okay, so I already found my C. I just picked 2 for a logic block when I connect one logic block up. Now when I go to level 2, I have C times gates. Well, it's not really gates, I'm doing logic blocks. And now I've got 2 logic blocks I'm hooking up, not 1. And my rent exponent I said was 0.5. And I just picked that, right? Seemed like a good idea to me. Okay, that number is approximately equal to 3. Okay, it's some fraction, but I can't make fractional wires, so I make 3 wires. If I go to the next level, so W of level 3, okay, so that's these wires. The amount of stuff that I'm connecting, well, first I have my constant 2. Then the amount of stuff I'm connecting is now 4 logic blocks, right? That's the amount of logic I'm hooking up to these wires. So it's 4. My rent exponent is 0.5. And that's exactly equal to 4. Okay? So that's what I drew. Okay, now let's say I want to map some circuit into this. And let's say my P circuit, it's got a lot of random logic in it, a lot of control logic. So let's say our P circuit equals 0.75. Okay, so now let's talk about what demand for interconnect the circuit has. So at level 1, it just has, level 1 has 2 logic blocks. They each have 1 input, 1 output. So the number of wires it needs is 2. Okay, so that's good. If I got that wrong, I really screwed up because I didn't even hook up. I made a logic block with 10 inputs and I made 2 wires. And that would have been probably somewhat stupid. So I got it the right first level. Okay, at the second level of hierarchy, that's my constant basically. But now the amount of stuff that I'm connecting in my circuit is twice as big, right? It's now 4 logic blocks. And my demand for interconnect is growing to the 0.75 power. Okay, so that's equal to 3.4. Okay, so 3.4 is more than 3, but it's fractionally more than 3. Maybe it's okay. Okay, so maybe I'll get 3 signals will be enough, and I'll be able to connect this part of my circuit to that part of my circuit. But already the CAD tool is probably going to have some trouble, and it's a bit dodgy. If I keep going at D of level 3, okay, I have my constant of 2. I now have 4 times as much logic, right? 4 logic blocks worth of logic to hook up. The rent exponent is still 7.5. And that's equal to 5.7. Okay, so this half of my circuit wants to send 5.7 signals to this half on average. I built 4 wires. This is unlikely to work now. So at this point, it's probably not like the CAD tool got lucky or rounded down. I need more wires. And it's going to unroute. Okay, so CAD tool is basically not going to be able to solve this problem. So what does the person do now? They probably blame the CAD tool. That's the first thing. They never think to blame the person who made the hardware, but they blame the CAD tool. But after he or she calms down, what are they going to do? What do you think?
Probably break up the design, which makes it like you have to shrink the design so that you're not using as many logic blocks.
Yeah, they really don't have any great options. So they basically could buy a bigger chip, right? That's one option. Often these chips have already, in the FPGA industry, usually the chip's actually been put on the board already, like for the big designs. Like you're going into some big system, they've already put the chip down. You can shrink your design and essentially underuse the chip. Like, don't fill all these logic blocks, and then you will still fit. And yeah, that's what people will usually do, right?
I think there's I guess Jason was telling us about an example of like a design chip years and years ago where the routing was poorly done where you could only ever use like 7% of the chip.
Xilinx is, yeah. I think Xilinx chips, that definitely happens, right? Like, yeah, that I don't know exactly which Xilinx chip that is, but definitely those things happen.
It feels to me like it's kind of running into that situation because you don't have enough routing.
No, that is what happens. You're exactly right. They basically, the routing's expensive, you don't want to put it in, you assume circuits are more local, or maybe you didn't even think about it, right? So you just don't even know some of these things, so you just take the wiring out because you save it. And yeah, it doesn't route well. So they're not alone in that. There have actually been many FPGAs where it's like, as a cost reduction measure, some routing came out, and then, you know, a year or two later, disaster befell people. But the most logical thing the person can do, they can't change the chip, they space out their design, okay? So let's see how much they have to space out their design. Okay, so we can underutilize logic to route. Okay, and maybe if we have to just underutilize it by a little bit, it's fine, right? This was a kind of hard design. It has to underutilize it by some amount. You know, a big part of what you're paying for in an FPGA is the routing. So, you know, that may happen, that you're limited by the routing and you have to space things out. Okay, so when do you have to do this? Basically when the rent exponent of the circuit is greater than the rent exponent of the architecture. Okay, so we need 5.7 wires, so basically 6 wires to connect, you know, 4 logic blocks in this half to 4 logic blocks in that half. And we don't have it, right? We only have 4. So let's look at what if we went up one more hierarchy level in the chip. Okay, so I haven't drawn this, but I could take this whole thing, mirror it down here, and I would actually connect those 2 halves with something that was the level 4 interconnect. So if I do that, it's just my constant 2. Now I've got 8 logic blocks that I'm connecting on each half. And my rent exponent that I was using in my architecture was 0.5. So I would get actually 5.7 wires. So the level 4 wiring, again, I haven't shown this, but the idea is that it would, let's see, where would I draw the level 4? The level 4 would basically be here. And I would draw it with 5.7. I'd round that off to 6 wires. So that actually has enough wiring for this circuit, but has enough wiring at the 4th level of hierarchy for what I needed at the 3rd. Okay, so that actually means that I have to actually take these 4 logic blocks that I would have liked to have just put here and connected them up to 4 over here. I actually have to take these 4 and essentially spread them across all 8 of these. Okay, and then the other 4 I wanted to connect to, I spread across 8 down here, and now I'll have enough wiring to connect them. But I had to spread it out by a lot. I basically said I could only use half my logic. That's the amount I had to spread out to go up to the next level of hierarchy, get the routing I need. So it's not a small spread out factor when your circuit has worse locality or a higher rent exponent than the architect expected. Yeah?
I'm wondering if Cattle's ever tried to calculate like the context one of the architecture and the application that's being mapped onto it. Try to do something where you can, I guess, figure out if you have to space out your design or not.
They don't directly calculate the rent exponent usually, but they do try to figure out if they have to space out your design. So CAD tools have a bunch of heuristics in them to watch for congestion. And they can, so a really big circuit usually doesn't have just one rent exponent. It may have control logic that has like a poor rent exponent and then some data paths that are better and has different modules. So if you have some part of your design that has a higher rent exponent, then yes, the CAD tool can figure out this is like overusing the routing and space just that out. Does that make sense? And yeah, CAD tools do try to do that. They usually don't do it by directly, like by calculating a rent exponent, because it's actually hard to find the rent exponent of a circuit. The way you normally find it in practice is you actually run designs through a CAD tool and you analyze the results. So while this relation holds, to figure out, like one of the ways to figure it out is to actually run it through a CAD tool and look at it. Another way would be to take just the hierarchy of the design and look at it. But CAD tools can essentially sometimes do a bit better than you would think from just looking at the hierarchy of the design because they rearrange the logic some. So a better way to get the rent exponent is actually look at what happens after the CAD tool has implemented the design and how far do signals go and so on.
I guess another part of the follow up is how relevant is the rent exponent if you're not using the hierarchical
I'm going to show you it actually still matters in island style. So I'm basically using this to figure out like what do we need for hierarchical FPGAs, but this actually has meaning no matter what. Okay, so it turns out that no matter how you make your chip, you do not like these high rent exponents. Okay, whether it shows up in your hierarchy or it shows up in more general routing demand, the high rent exponents are bad. Okay, so let me just write this down now. So basically, that amount of routing supply equals the demand from our circuit with 4 level 1 units or logic blocks. Okay, but it's actually at the hierarchy when we have 8 of them. So it means we can only use half of our logic if we're going to scale to that size. So we use only 4 of 8 blocks, basically, like half of our logic. Okay, so there's a long analysis to show that the locality of a circuit affects how you build these hierarchical FPGAs, and that there is a significant cost for circuits that exceed your rent exponent. Okay, I probably shouldn't have erased that. All right. I'll probably bring it up on the picture then. Okay, so another negative, which you already talked about, is for this kind of architecture, is the long wires at the upper hierarchy level. Okay, so high R and C, so they're slow. We could put buffers in the middle of them, but they have to be programmable buffers that can kind of go one way or the other. That's going to add area. Okay, so we need to rebuffer. So in a modern chip, you just can't go halfway across the chip. So like at the upper levels of the hierarchy, a strict hierarchical FPGA would have wires that are like spanning half the chip. Those are like just unbelievably slow nowadays. You can't do that. You have to put buffers in them. So we'd have to rebuffer those long wires, which would cost us area and power, and it would also break the partitioning abstraction. So part of what we liked about this was that we could kind of keep our CAD tools simpler. We could use a partitioner. As we start putting in like programmable buffering and so on, well, that starts to break down. A partitioner is probably no longer the right tool. So that's taking away part of our motivation for doing this at all. Okay, like we don't have a constant kind of wire count or delay increment whenever we chop a signal between 2 partitions. Okay, and then one last thing. Okay, so somebody kind of already mentioned this, that it takes blocks that are far apart are slow. And some of that's unavoidable, but let's look at whether we're doing as well as we could. Okay, so let's make a hierarchical FPGA like this. Okay, so let's say this block A wants to talk to this block A prime over here. Okay, so it connects to its level 1 wire, so it turns on that switch. Connects to a level 2 wire, so it turns on this switch. Connects to a level 3 wire, so it turns on this switch. Actually, I shouldn't go that way, that far. Okay, then I got to go down through another level 2 wire, through that switch to a level 1 wire and in. Okay, so my signal path went like this. Okay? But these two blocks are not physically that far apart. Like, they're only that far apart. So, you know, physics says there's going to be some limit how fast these can go, but it could have been better than this, because this forced me to kind of take a circuitous path. If I was going from here, from B to B prime, okay, well then I would come out, I'd go here, I'd go here, I'd go here, and I'd go here, right? And that's pretty minimal. Like it's a long route, but it kind of had to be, because they were on opposite sides of the chip. But here, these two things were not that far apart, but my routing architecture forced me to make them far apart. So I kind of lost an opportunity. Okay, so some blocks that are physically close are far in the hierarchy. Okay, and so it's kind of a missed opportunity, right? There should have been a way to connect those things faster than I did. Okay, so all of these things lead to an alternative style, which is called island style. So hierarchical is still used. I showed you some examples of it, but island style is dominant. It's the number one kind. Okay, so let's put up new kind of architecture, island style. So the intuition behind hierarchical FPGAs is circuits are hierarchical, so let's build that in circuits. The intuition behind island-style FPGAs is chips are two-dimensional. What can we build that is two-dimensional, right? Like, what can we efficiently create that is two-dimensional and could get signals all over a chip pretty efficiently? So it kind of starts the opposite way. What can I build efficiently on a chip, and then how can I morph that to match the needs of circuits? So island style is a 2D structure. So you basically have logic blocks, and they're kind of islands that are surrounded by a sea of routing. Okay, so I put some wires in these channels. So I might have some short wires that only go one logic block, maybe some longer ones that go two. And I do that in all my channels. Okay? And I'm going to do it in my horizontal channels too. Okay, so I built some length 1 wires. I built some length 2 wires here. I need to connect to them. So I build programmable switches that allow me to connect my logic blocks to at least some of these wires. Okay, so now the logic blocks have programmable switches to connect to these wires, and then I need to build some more programmable switches to connect the wires to each other. And I don't connect them all to each other, right? Whenever they cross at a routing, two routing channels cross, I take some wires and connect them to each other. And creating good patterns for that is complicated. But those dashed lines are basically programmable switches. So basically I could come out on, let's take an example here. I could take this logic block, connect to this wire using that switch. I could turn on this programmable switch to come down here. And that actually gets me nowhere because nobody connected to it. So maybe I'm going down further. I could take this programmable switch to get over here. And that gets to this wire, and I could get into this logic block. Okay, so I've made a connection between those two. And if I needed to go over to this guy, in the way I've drawn this architecture, I think I'm in trouble. Okay, so I probably haven't got enough wires or enough switches because I can't actually see a path that gets me from this logic block to that logic block. So I probably need to put more switches in or more wires. But hopefully you get the basic idea. Okay, so I got routing channels that surround a block. Okay, so some terminology. I have these routing channels. So this would be a routing channel. Okay. They're filled with wire segments. Okay, so this would be a single wire segment. This would be another wire segment. Or sometimes we just call them routing wires. And we usually make several different, we have to prefabricate all these in an FPGA. We usually pick several different lengths and build a few wires of each of those. Okay, so here I've drawn some wire length segments that are one logic block and some that are two. And in commercial FPGAs, you might have 6 or 10 nowadays. Types of wire, like 1 logic block, 3 logic blocks, 7 logic blocks. I don't know if anyone's done 7. They don't necessarily do prime numbers, but 1, 3, 6, those kinds of numbers. And we'll talk about why. We'll look at some papers about how do you select that. But there are trade-offs, right? There are cases where long wires are more efficient, some cases where their short wires are more efficient. So because we have to build them all in advance, we usually build some of each. And then we have programmable switches. Okay, and those are often divided into 2 parts. So the ones that connect wires to logic or other block IOs. Okay, and those are often called connection blocks. And the other kind of routing switches we have connect routing wires to each other. Okay, and then the last thing, piece of terminology, is the number of wires in a routing channel is usually denoted by W. Okay, so the channel width is W wires. Okay, so if you look at this and kind of analyze it qualitatively, what do you think is good about this? Any positives or any negatives? You see negatives right away, that's fine too. What do you think?
I guess the positive is that there's a lot of flexibility in the sense that if you have different things that are close together, then usually there's some route that allows you to go pretty close by, and then you can also have, even since some things that are corner, if there's enough routing segments, you can always sort of connect them.
Yeah.
There's the flexibility. I guess the downside is if your W is high, there's a lot of power usage because there's a lot of switching and a lot of connections. If W is low, then maybe there's a lot of compression.
Yeah, so that all makes sense. So you're right. One of the things I didn't like about hierarchical FPGAs was sometimes there were logic blocks close together and there was no short path between them. If you choose these wire lengths well, you have some short and some long, that won't happen, right? And you choose your switch patterns well. So I chose it badly because I can't figure out how to connect that to that. Okay, so I failed the FPGA architecture test. But assuming I could have done better at that, if things are physically close, there's a way to connect them with relatively low delay and not too many wires and so on. So it's cheap. You're right so maybe I'll write that down. So one of the big positives is this kind of follows physics. Okay, so physically close. If you've designed the architecture well, you'll have some fast routing choices. And basically that wasn't always true in hierarchical FPGA. Now, weakness could be, in early island-style FPGAs, they actually only had short wires. Okay, so if I had to go a long way across the chip, and you have to like go through, if I have to go n units over to the right, and I have to go through n of these programmable switches, stitching together like these wire segments to get there, that's actually pretty slow. And it also means I had to build a lot of programmable switches, which has more area. So if I only had short wires, you actually have a problem of going long distances. But that's why they put in some longer wires. So as long as I have some of these longer wires, I can still get across the chip pretty efficiently. Is there a comment? I think I saw somebody. Yeah.
And in that like first paper we had to read, like the first one of the course, like survey, or not survey, the historical thing. Anyway, the author had said like, oh, also by putting in the like longer wire segments, well then it placed like a bit of, or gave a bit of slack to the placer, whereas if it did a bad job, well now even stuff that is misplaced like far apart can still like,
I agree. Steve Turner is definitely on the hardware side, because so it's a good point. So basically, it is giving more freedom to the placer, but you're right. In the case where you only have short wire segments, it's kind of deadly to have things far apart. The reason I'm laughing is because it's like the classic CAD architecture. So if I put only short wires in, the placement engine screws up. So actually, I was on both the hardware architecture and the CAD teams, but it's like, well, it's kind of interesting. You could alternatively argue the hardware team screwed up, right? So, but there is a tendency to say, well, the placement engine should be able to exploit this. You just need to work harder on the algorithms. So, when I was at Altera, I had many customers explain to me like that what they needed was they needed the placement engine to find the critical path and just put it right beside each other. So, it turns out it's actually much harder than that sounds, right? So, but yeah, it does make placement easier. You're right, because it's not so catastrophic to have a long connection. So your CAD engineers do love long wires too. The longest wires in at least in Altera FPGAs, I'm assuming Xilinx does something similar, are basically architected to be the wire length that will get you across the chip fastest. Like making a wire that goes all the way across the chip is actually really slow because the R and C build up. So there's an optimal repeater distance of how often should you rebuffer. And the longest wires in an FPGA are usually close to that. They're usually a bit shorter than that, it gives essentially as easy a time of it as to the placement engine as you can, right? Like if you made these things far apart, at least we'll try to get there as fast as we can. Now, nowadays, that's still many clock cycles, right? Like to cross a modern big FPGA would take you a whole bunch of clock cycles. So it's still fairly bad if the placement engine puts it all the way across the chip. Okay, so another positive of this is that this is actually scalable. Okay, so what do I mean by that? Well, so it's physically scalable. I can basically lay out a tile, and I can repeat it over and over again. Okay, so I can clearly make if you give me a bigger silicon area, I can make a bigger chip. If I shrink everything so my logic blocks get smaller, my running gets smaller, I can stamp out more copies, I can make a bigger chip. But what I mean by scalable is when you do that, can you actually route larger designs? Because that's what you really care about, not could you stamp out more things. Okay, so to check that, let's do rinse rule again. Okay, so we basically have, let's look at an array. So we'll look at a really small island style FPGA. Okay, and we'll draw a box around this 2x2 grid. And we're going to define the number of rows or the number of columns as m. Okay, so I've got an m by m array. So that's like my logic. The amount of logic I have in this is basically m squared logic. So how many wires do I have coming into this? Well, I have a channel with the width of W. Okay, maybe I'll draw it on this side. Okay, so I've got W wires coming in, and I've got, say, a channel above there and a channel above there. So I've got M of those channels on each side, and there are 4 channels. Okay, so if I just say, how many signals could I possibly get into this from the outside world to this array of logic? It's basically 4 times M. Okay, that's just how many channels I have, 4 sides and M channels high, times the channel width, which is W. Okay, so that's how many wires enter. Where are they entering from? They're entering from like the rest of the chip. Okay, so I'm taking it, or the rest of the system. Okay, so that, you can say that many enter, but let's say leaving. Leaving is probably makes more sense for Rent's rule. It basically is the same. So that's how many signals I can get out of this thing. It's also the number of signals I can get in, but it doesn't really matter. So let's call that the supply. Okay? So let's use Rent's rule again. So the number of terminals, or number of signals I need to get in and out of this thing, is some constant times the amount of logic to the p. Okay? I'm just going to say that's some other constant times m squared. Okay? Because that's how much logic I have in this. It's like I got a certain amount of gates that this thing can implement, this logic block, and I've got m squared of them. I just changed my constants, and I can now ignore the fact that this is like logic blocks instead of gates, right? So it doesn't matter. Okay. Okay, so that's how much logic I have. Rent's rule says that the number of terminals should grow with that to the p. Okay? Okay, which is, I'm just going to rewrite that to make it neater. So m squared to the 2p, or m to the 2p. And I'm going to define that to be W demand. Okay, so that's how many wires I need to get in. This is how many wires I have. And what we want is that the amount the circuit wants to get in to some block of, some m by m block of logic. Yeah?
Where did the 4 come from?
4 comes from 4 sides. So 1, 2, 3, 4. No, so the m comes from the fact that there are, so I am basically saying every logic block comes with a routing channel above it and to its right. So I get 1, 2 routing channels if m is 2. Does that make sense? But if I change m to 4, that would be a 4. The 4 comes from just 4 sides. So good question. Okay, so I want my W demand to be less than my W supply. Okay, and that's true. We'll just substitute in what we have. Okay, so we set our W demand. All we care about is basically how it grows with the array size. We're trying to see if we make a bigger and bigger array, is this going to work? So we've got C primed m to the 2p. Okay, so the p comes from a circuit. The m comes from how big we made our chip. And that has to be less than the amount of wires we can get into that array, which we said was 4 times m times w. I probably shouldn't have used w to mean 2 things, but let's say this is like w FPGA. Okay, that's like the wire, the width of these channels. Okay? Okay, so if I basically do a little manipulation on that, okay, so let's just manipulate that a little bit. We get C prime over 4 times m. And I'm going to take m to the 2p, divide by m. So that becomes m to the 2p minus 1. And that has to be less than our WFPGA. Okay, what we built in the routing channels. Okay, so what I'm trying to do is see, well, what happens? How wide do we have to make these channels as the array gets bigger and bigger? So let's say the rent exponent is equal to 0.5 or less than that. So if it's 0.5, then 2 times 0.5 minus 1, that's 0, m to the 0. Okay, so for all circuits where the rent exponent is 0.5 or less, I never have to increase the channel width. Okay? I can just keep stamping out the same layout tile on bigger and bigger chunks of silicon, and it's still going to route. Okay, at this point, you actually could blame the placement engine if it doesn't. Okay, it'll be fair. As long as the placement engine does a good job, then it would always route. Okay, so that'll be constant W as we increase the array size. And there are a fair number of circuits and data paths that actually fit that. So this is a nice result. You can make them bigger and bigger FPGAs. We don't have to widen the channel. It means we can have kind of the same fraction of our area goes to routing, even as we make the chip bigger and bigger. So that's quite scalable. It also means we can make bigger and bigger chips without doing a relayout, right? Just take the same tile and stamp it out, 10 by 10 array, 100 by 100 array, 1,000 by 1,000 array. It's all going to be good. Okay, but not everything has that. Let's say we said random logic, control logic has a P more like 0.75. So if we plug 0.75 in here, we get 2 times 0.75 minus 1. We get that the WFPGA, in order for this to successfully route, has to be proportional to the square root of m. Okay, we get m to the 0.5 here. Now, the amount of logic, basically the logic that we have is actually m squared, right? We have an m by m array, so the amount of logic we built is m squared. So that's what we kind of sell our FPGAs as, this capacity. So let's rewrite this as a function of capacity. So W has to be proportional to n blocks, right? The FPGA capacity in logic blocks to the 0.25. Okay, so I just did a change of variable, right? M is equal to the square root of n blocks, so I can rewrite this as n blocks to the 0.25. And this is not bad. Okay, so for circuits that actually have relatively poor locality, I am going to have to increase the channel width, or I'm going to get into trouble, but it's relatively slowly increasing. I could increase the size of my chip by 16x, and I only have to double the routing channels. I'd rather not do that. It means less of my area is logic, but it wasn't too bad. This wasn't catastrophic. So it's a slowly growing function. And in practice, usually you won't have a whole circuit that's 0.75. You might have some pieces, and that's where you get CAD tools essentially going, okay, this part is looking a bit dodgy, spread it out, right? So they'll try to locally underutilize part of the chip rather than all of it, and that will help them basically, without scaling the channel width so aggressively, still fit the vast majority of designs. So in practice, W goes up slowly as you make your FPGA bigger and bigger, but it's a slowly growing function. So and normally what happens is for a whole generation, so like Xilinx Versal, it'll have a range of device sizes, and they'll use the same channel width for all of them. So over a factor of 10, they'll just wind up with the smallest devices are a bit easy to route, and the largest ones are a bit hard to route. But this function, which is somewhere between constant and like, maybe a fourth root, is slowly growing enough that for an entire family, they can usually just say, we'll just lay it out once and it'll be fine. If you can make your CAD tools better, you can effectively push it a little further. So there's actually a big upside to making your CAD tools better as well. Okay, so in practice, if you have good placement, then W grows pretty slowly. Another thing it's kind of a negative, but it's just a factor of life. So this architecture works well. It's more scalable than hierarchical, but it needs good placements. If you have a really bad placer, okay, so this is quite bad, but a bad placer, P actually is approximately 1. Okay, like you just wind up with like super long connections all over the place, and it is disastrous. Like then the scalability is terrible. There are many routing choices. So in the hierarchical FPGA I showed you, once you had a partitioning or a placement, the routing was fairly constrained, right? You had to cross these hierarchy levels. You could choose about exact wires, but how you were going to get there was pretty constrained. With that island-style FPGA, there's a huge number of ways you can connect things, which can be a strength, but it also means you need a good routing algorithm, right? If you don't have a good routing algorithm, it won't find good routes because there are lots of bad routes mixed in with the good ones. So you need a good and timing-driven router. Okay, so what timing-driven means is that the CAD tool is analyzing what are the speed-limiting paths of your circuit and giving them the best options. Okay, so it's not enough to just try to give everybody pretty good options. You need to actually know what parts are limiting your speed, like could wind up on the critical path, and give them the options they really want. Because not everything is going to get the option they want with all these different wire lengths and so on. Okay, because basically it's a more diverse routing architecture. Okay, and we're going to talk about this in a bunch more detail in the rest of the course, well, later in the course, because island style is dominant now. So when I first joined Altera, okay, so my history with Altera was I had a startup that came out of my PhD research, and we were essentially a company that was partnering with FPGA companies to build them better CAD tools and better architectures. And Altera was one of our customers, and they had hierarchical FPGAs. And we targeted our CAD tools at their FPGAs and got actually much better results. And the way we did it, it's a few techniques, but one of the key things is we essentially ignored the hierarchy. Like, well, we understood the hierarchy was there, but we didn't use partitioning. We basically said there's enough variation now in delay with these long wires. Even if it's a really long wire, if I get two things pretty close on it, that's actually faster. There were enough things that weren't well represented by a partitioner now that we basically did it without partitioning. And it was more timing driven, and it works better. And then we were acquired because we told them your chips are the wrong chips for our CAD tools, right? You should let us design your chips. And we gradually found out they actually believed that, but they also, at the executive level, were like, there's no way we're going to have an external company developing our CAD tools and our chips and selling them to whoever they want to. So we came in and we architected the next generation of Altera's chips, which is called Stratix. So the previous generation was Apex, which is hierarchical, and the next generation was Stratix. And they actually had an overlap. So I'll show you a slide on this later. But there was one generation, same process technology. I actually had a hierarchical FPGA and an island-style one. And Stratix was the island-style one that the team here in Toronto developed. And it was twice as efficient. So an area delay product, which we already saw as like a measure of like throughput per silicon unit area, was 2x as good in the same process technology as the hierarchical FPGA. So that's the only like really rigorous comparison I know of to these two things, and it's like really rigorous. Like you spend like $100 million on each project, right? Like it's difficult for academics to do that kind of A/B study. So island style really does work better, but you do need good CAD tools. Altera internally had actually evaluated an island style FPGA themselves and concluded it was a bad idea. But after we showed it was a good idea, what they concluded was actually it was their routing algorithm. Well, it's both their placement and routing. Their routing algorithm wasn't timing driven enough. So with their CAD tools, they came to the conclusion that it wasn't a good idea. But this is one of the challenges with architecture where you always have to run everything through a CAD tool. It essentially wasn't really a true result. It was a true result for their CAD tools, but it wasn't a true result if they were able to develop CAD tools that could fully exploit that architecture. it's actually always a challenge, actually, because every CAD tool has a certain bias, but it was like an interesting one where they had actually come to the wrong conclusion a few years before because of that. Okay, but the end summary is, at least for big chips, island style dominates. For these embedded FPGA IP cores, where it's relatively small, hierarchicals can still be okay, and there are commercial examples of that because they don't get the really long wires. They just don't scale to the really big design. Okay, so let me ask you one last thing. Okay, as I promised, I'll finish up on time today. So what about a hybrid? Okay, so I told you island style dominates, but is there anything we can take from hierarchical? Sometimes with engineering, we get the best of both worlds if we can combine things. Sometimes we get the amphibious car. So what do we get? Is there a way we can get the best of both? What do you think?
I guess because with hierarchical FPGAs, it's very good for partitioning. You can partition certain parts of the design. Like you could have several island-style sub-FPGAs and then connect them through a hierarchy.
Okay, so you want to make small island-style FPGAs, right? Okay, so that's my island-style FPGA. But then on the same chip, now I'm going to connect those through hierarchical interconnect. Yeah, so that will make a hierarchy between those. So these connect, and then there's a hierarchy that goes to these guys, and so on. Is that right? Okay, so I'm going to go to the class. Is this like best of both worlds, or is this amphibious car? So sorry to pick on you, but what do you think? Who thinks best of both worlds? We got a few? Okay, who thinks amphibious car? Well, one or two brave souls, the rest are like, I don't know. I don't even understand these questions. So, what do you think?
I guess the one thing that you can make it, like, to me, the reason I would go with that is, like, for one example, you can, like, you don't need to use the entire hierarchy, and the design can fit on, like, one subject.
Yeah.
You could also have, like, kind of clever interconnect, or sort of more sophisticated interconnect options, like things like NOx across the hierarchy, which can make the interconnect, like, faster.
Yeah, so NOx are good. So we'll get to those later in the course, but you're already ahead. So I guess, okay, so I guess what, so okay, so you're bringing in NOx and so on, which hold that thought. We'll come back to that. So if we start talking about hierarchy as, I would say NOx are kind of a different beast though. They do give you a higher level of system level interconnect, and yeah, I agree with you, they're useful. But let's talk about just kind of these programmable wires and how we're not going to get to NOx yet. We're just connecting the architectures that we've thought of. Yeah, so I'm gonna say amphibious car. The reason is hierarchical was good for small things, right? When the wires were still pretty short, it can work pretty well. But when the wires start getting long, that's where we really start having problems that we don't know how to resolve. These wires are slow and expensive, and we just kind of can't get rid of them. So you've basically made an island-style FPGA, but they're for the little parts, and then for the big parts, you said hierarchical. So I think you're kind of taking the weakness of hierarchical and really hammering it. So, yeah.
What if you use the hierarchical stuff for like when you have like they're trying to do ASIC emulations and you use like multiple FPGAs, you connect the different FPGAs in a hierarchical style of like network.
Yeah, that actually makes sense at that level too. Like you could use network switches, and that might be at that point essentially your wiring is kind of more expensive than your switching, so you're trying to minimize hops. And yeah, that's a pretty reasonable way to do that. Yeah, what do you think?
So for hierarchical, if you start from, because it's fractal-like, if you start from the highest level, then the wiring distance is equal to any point, which means you can use it for clock signals within like the same clock region.
That's true. So clocking does tend to be more hierarchical. So you're right. So yeah, so these are actually good answers. So there are regular forms of hierarchy like clocking. There's like NOx. We'll see some other forms of hierarchy that we bring back in. Yeah, what do you think, Alex?
What if you're also dealing with really large chips and you're dealing with interposers where crossing is actually quite expensive, so you might want to do a hierarchical approach there as well.
Maybe, although I'd say that the interposer cuts the whole chip, so it's difficult. I haven't seen that be super hierarchical, right? Because you still have a 2D stripe. I'm trying to think of how that would work exactly. I guess if you, yeah, I'd have to think.
You have more than just two chips.
Maybe that gets into the emulation style as well.
I guess like in the other way around, where you have like small hierarchies and then you connect them to sort of islands.
Yeah, and that's actually what's done. So the dominant form is a hybrid. The hybrid is mostly island style, but basically at the lowest levels, like the small things, hierarchical works pretty well. So usually people will build like logic blocks and function blocks that have a bit of hierarchy in them, maybe 1 or 2 levels of hierarchy. And then so they don't actually usually hook directly a lookup table to the programmable routing. like the main programmable routing in an island-style FPGA.
I guess you'll do it through Muxin.
Yeah, well, what they usually do is you take some of the basic stuff, like LUTs, and you'll combine them together with some muxes and some local interconnect to make a logic block. So essentially that logic block is like 1 or 2 levels of hierarchy. And it's essentially simpler than using island-style interconnect, where you have to find complicated paths between these LUTs. You essentially have a simpler, they're all just wired together through multiplexers of some type. And because they're all pretty close together, it works well. And it does simplify the job for the CAD tool. So let me erase this and draw this quickly. Okay, so basically what they usually do is use hierarchy, or hierarchical at the lowest levels of hierarchy. Okay, so let me show what that looks like. And I guess the reasons are the wires are still short at this point. So let's take the logic block, for example. You can group LUTs, but usually we don't call them LUTs anymore. Once we add flip-flops, we call them basic logic elements. It's like a LUT plus a flip-flop, maybe a bit more stuff. And you group those into logic clusters, which we still call logic blocks. Okay, so what does that look like? So you have this BLE, which is like a LUT and a flip-flop, and you have a bunch of those. So you might put recent chips, this might be anywhere from like 4 to 32 of these that are put together, and they have some local interconnect. So their outputs can feed back into all or some of these inputs, and you also bring in some inputs from outside. Okay, so this goes out to the regular main routing. And you bring some inputs in from outside, and you can connect those into these basic logic elements as well. So you basically get like a local interconnect structure here that's relatively simple. It could be a full crossbar or a very simple 1 or 2 level hierarchy. So you have this local routing. These are not just LUTs, they have flip-flops in them, so you bring a clock in. Okay, and then all around this becomes your logic block, and then it connects into your routing out here, like your island-style routing. Okay, so the advantage of this is it can simplify some of the CAD tools. So the wires are short enough that they work well. And we can still cluster things into this, which is essentially a form of partitioning where you create a lot of partitions at once. So it still helps us make the CAD tools a bit simpler. Okay, so the positive, it's local routing fast. For this n less than or equal to something like 32 or 20, depending on who you believe. So Altera has slowly been making this n a bit, well, yeah, okay, I guess there's no consensus about how big you can make this, but you can make it some moderate size. Okay, so the other positive I said was it simplifies the CAD flow some. Okay, so we can cluster these little BLEs to these somewhat larger logic clusters. So that can make a smaller placement problem. Another positive of this is essentially we get the notion of sort of word-wide logic. So we're bringing in, LUTs usually use all sorts of different signals. Okay, so they may share some, so we're going to try to put LUTs that have some of the same inputs together. It's more efficient. But clocks usually connect to a whole lot of things. So we don't need every flip-flop in here to select its own clock and route its own clock in from the regular routing. So what's commonly done is you'll bring in maybe one or maybe two clocks into this whole logic block, and they go to all the flip-flops. So it's kind of like you've got a bit of word-wide logic. You have individual bit-wide signals that go to like the inputs of the LUTs, but the clock goes to everybody. So this logic block, or this lowest level of hierarchy, gives us a natural way to do that, to have some signals that kind of are shared or fan out. Okay, so we can share resources that need less flexibility. Okay, so if we did island style all the way down to the end, where we're connecting individual registers and LUTs up, we would be routing, clocks and clears and so on to every single register with island style routing. But we can essentially instead say, well, let's just broadcast it. We got like one clock wire that goes to all of the flip-flops of this logic block. Our clustering step, the thing that decides what goes in a logic block, has to make sure it doesn't mix and match clocks, but that's not too bad. It's not too much of a constraint. Okay, so clocks would be one example where it's not too bad to share, but that's not the only one. Clock enables, synchronous clears, asynchronous clears. All those signals tend to be kind of word-wide. Okay, so we've got all these signals on a register, right? Not just the D and the Q. But also the clock enable, the clock, the synchronous clear, etc. And basically all these ones need less flexibility. They tend to be shared across large numbers of registers, banks of registers that kind of belong together. So we put them all in a logic block and give them a more restrictive routing, and it's more efficient. And the last thing that's actually good about is we don't, in an island style FPGA, we don't really just have logic blocks. Okay, so we'll have a logic block, and we put wiring in between them. But then we put in RAM blocks, and we put in DSP blocks. And those blocks tend to be much close. They're not the size of a LUT. A LUT and a flip-flop would be tiny compared to a RAM block or a DSP block that has multipliers in it and so on. But once we combine a bunch of LUTs and flip-flops together with some local routing, we wind up with something that's actually kind of more similar in size to the RAM blocks and DSP blocks we're interested in. That actually makes it a lot easier to make this island-style interconnect so it works with everything, right? Otherwise, we'd kind of have a mess if we were trying to make these fairly chunky blocks connect to the same routing that these tiny LUTs are connecting to. And the tiny LUTs were connecting with really short, tiny wires. It's difficult to even think about. So this using hierarchical concepts at the lowest level gives us some good benefits, and then we combine that at the higher levels with an island-style architecture. I think I went 1 minute over, so I'm going to wrap it up there. Yeah. Yeah, so I said word-wide. I mean, an FPGA doesn't really have a word. It's whatever you ask for. But basically, when you write your RTL, you'll usually have like a whole register, 32 bits wide, that's the same clock enable. Kind of maps well to a logic block. Does that make sense?